Today we're going to talk about how to represent lines in 3D space. We know how to represent planes. Now we want to know how to represent lines. First, let's refresh on how we represent lines in 2D space. So remember, lines are defined by a direction and an initial position or position in space. So in the plane or 2D space, we've conventionally learned that lines have slope and they have an intercept. I'm going to call it an initial y position because once we move on to 3D space, we're going to have to generalize to an initial position and then a direction. Notice that there's a single equation that can represent this line in 2D space. We have y and x. We have a linear equation relating y and x. Another thing to note is that this initial y doesn't have to be exactly where x is equal to 0. We can represent a line also by, say, our initial position is here on to the left of the y-intercept. If we let this point over here be the initial position, all we have to do is we just have to horizontally or vertically transform our equation here, and eventually it would simplify to the same equation that represents the line in which we let the initial position be the y-intercept. So what I have on this right tab is a 3D version of Desmos, and I'm going to graph that same idea with lines in space on this in 3 dimensions. So first, let's just notice again we have a line with an intercept and a slope, and we can graph this in a single equation in 3D. The thing is, once I extend it to 3 dimensions, we have our plane, but we also have the z-axis, which gives us our height in our third dimension. Notice that this line is only in the plane. It's restricted to only 2 dimensions. The thing is, we want to know how to represent all lines in space, meaning if we wanted a line that's slanted or a line that's like 5 units up on the z-axis, we want to know how to represent all lines in space given any direction and any initial position. The thing is, what I'm showing right here actually isn't a line. This is y is equal to mx plus a number. However, we're in 3 dimensions, so we're missing our third variable z. And when I press extend to 3D, this is actually what's happening in 3D space. So if I want a single equation for a line, it's actually going to be a plane. What this is saying is y equals mx plus y is equal to some value. However, z is going to be any value. So z is any real number. Imagine an infinite number of lines that are parallel to this line stacked on top of each other, and that creates this plane. So this is an infinite set of lines creating a plane. So this is why we can't graph lines in 3D space as single analytic equations, which are just equations where you have one thing on the left equal to one thing on the right. I'm going to give another example. Say we have a function of x and y. No matter what way you put it, if we want a function in 3D space defined for 2 variables and we want a third variable to represent our line, we can't really do that, because in 3D space, if you want a linear combination of x and y, that means that function is going to be defined for all points x and y on this. So imagine on the plane, the function is going to be defined for every single point on the plane, meaning that it corresponds to a height in 3D space. So that's why it's a plane and not a line. What we could do with this analytic equation is we could add restrictions to, say, we let this plane only be defined for the points x is equal to y. So what this means is we just, along the line y is equal to x on the plane, this is where this function is defined. Now this does give us a line and what we want in 3D space, and eventually if we can do this for any line, but look what we had to do to the equation to give us that line. This isn't ideal, and there are other ways to represent a line in which we just put in inputs and get an output. So we don't want to do this domain restriction every time we want to represent a line. What I'm going to do to fix this problem is representing lines as vectors in 3D space instead of analytic equations. We have to imagine vectors as sets of points, and in this context, each vector represents a point in space with x, y, and z coordinates. So in general, vectors aren't just arrows. Vectors can represent anything as long as we assign an applicable context to it. In this case, vectors are going to represent points in space. Now, how do we start with representing lines as vectors in 3D space? First, remember how lines are defined in general. First, they need a direction and they need an initial position, similar to a slope and a y-intercept. So I'm going to imagine a line in 3D space. I'm going to assign a vector v to represent its direction. What this vector v is going to have, its components are such that it's parallel to the line L. No matter where you put v in space, it's going to be parallel to line L. So first we have something that represents the direction of L. Next, what we need is something to represent our position, and that's going to be this red line, which I'll denote by vector r sub 0. And I want to first introduce what we call a position vector. And a position vector is essentially a point in space defined by a vector. That means if we let the tail of our vector be at the origin and the vector ends at our point in space, that vector is going to be the position vector for that point. In this case, we let p0 have the coordinates x0, y0, z0, and r0 is going to be the vector that represents our point. Remember, vectors can represent anything we want. In this case, our vectors are representing points. So now that we have a direction and an initial position for our line L, we need to find a way how to put that together to represent any point on this line. And what I'm going to do is I assign another position vector to represent any arbitrary point on line L. And that's going to be point P with coordinates x, y, and z. So imagine we were on point P and we want to get along to any point from there along L. What I'm going to do is I add the direction vector v to point P0, and that's going to let me, depending on how much of v I add, that's going to get me to any place on L. So if you can imagine adding v to P0, remember v is parallel to line L. So that's going to get me to any point on L, if you can imagine that. Just imagine vector addition where you have, if I moved v to the head of point P, and I'm going to move along L this way. In general, what I just did is I let vector r, which is going to be the resultant of adding any multiple of our direction to our initial position, I let r equal to r0 plus any scalar multiple of v. I'm going to use Desmos to help understand what just happened. So right here I have a line, and if you're wondering, we're going to get to this in a few minutes, but this is the easiest way to, I guess, generalize a line in 3D space. We're going to get to how we can represent it like this, but just know this is the line that we want to represent. It's what we desire. So first we have our direction vector. Remember, this vector, this small gray one here, is going to be parallel to our desired line. So we have a vector that has the same direction as our line. Next, we need our initial position. So I'm going to click this, and here we have our initial position vector r0 with the point at its tail. That's going to be the point on the line. So we have a point on the line and then a vector that represents its x, y, and z coordinates. Look, we have, so P0, it's going to have coordinates x0, y0, z0, and then r0 is going to be the position vector starting from the origin to P0. What we're going to do now is combine our initial position with our direction vector to get any point on the line. So here we have this blue vector. If I zoom out a little bit, we have this blue vector that with the dot P, can't really zoom in on that part, but if you can notice the dot on the line, that represents point P, and then the vector that it's at the end of is the position vector for that point P. And right here, if you look at this equation, I have our vector r is equal to our initial position vector plus a multiple of our direction v. What this multiple is our parameter that we've given to our direction v. So we've just parametrized a line in 3D space. This t1, I didn't use t because I already used t in this desired line. This coefficient of v is going to be our scalar multiple that we multiply our direction by in order to get anywhere on the line from our position vector. An important thing to remember is that this equation, r is equal to r0 plus a multiple of v. What we're doing is we're adding vectors. To visualize that, I've added this vector here, which is pretty much adding our red arrow plus our blue arrow to get our purple arrow. This helps show that if we took our gray arrow, which represents our direction, and we took the tail of this and attached it to the head of our red arrow, that would give us our purple arrow. Our resultant would eventually be that point on line L. When we're dealing with vector addition, it's usually helpful to draw parallelograms that show head to tail addition. So what I've done is I removed, before I had the direction vector be of constant length, but remember our direction vector only cares about the direction. So it doesn't care about how long the direction vector is. As long as we're going a multiple of that vector, it's fine. I let the length be variable, so that helps in showing how if you imagine this last side to finish our parallelogram, it'd show how you add multiples of our direction vector to eventually result in our line. We've now found a way to express a line or points on a line how we want with vectors. So here I'm just changing t and it's allowing us to go anywhere we want on the line. The thing is though, I don't want to only use this one position vector for my initial position. Usually you're going to be asked to move this initial position all the way over here. The same way on the plane or in 2 dimensions, we let our initial position be on the left of the y-intercept. Say, I want to let this initial position be anywhere on the line. Fortunately, we can do that. Say I'm given coordinates for this initial position as x0, y0, z0. If you can visualize it, every time we want to move along this line, we're taking little jumps in a certain direction, no matter how big those jumps are. They just have to be in that direction. What that means is we're starting at this point and we're taking jumps that have x, y, and z components that are multiples of this direction vector. So how I'm going to change my initial position, x0, y0, z0, is I'm just going to take jumps in the direction of the line. In this case, if our direction vector has components 1, 3, 2, I'm going to start from my initial position and make sure I add multiples of 1, 3, 2 to our initial position 0, 1, 2. For example, if I want to jump one direction vector backwards, I do 0 minus 1, 1 minus 3, and then 2 minus 2. Notice how we're still on our line. And yeah, we're still on our line. And our purple vector is still going to result in a point on the line. So what I just showed is that you can still change your initial position, and as long as you go in the direction that the line is going in, you're fine. Another thing is that our direction vector doesn't have to have a set length either. The same way we can change our initial position, we can change how big our jumps are in each direction. So usually you're going to be given a direction vector that's a unit vector, meaning that it has a length of 1. So if you do the distance formula and take the square root of the sum of squares, you get a magnitude of 1. But in general, you can change how long you want the vector to be. As long as it's multiples of the unit vector and is parallel to the line, it doesn't matter. So what I did is, I'm not going to go into detail, but look at how I'm changing the length of our vector, yet we still have points that are along our line L. It's important to note that there's an infinite amount of ways to represent a line in 3D space. What that means is that you can take an infinite amount of initial positions, like say change where this red arrow is going to be, and that would give you the same line as long as the vector that you're adding to it, or how the jumps that you're making are in the direction of the line. You can't say the same for 2D, for lines in 2 dimensions with analytic equations, because eventually, no matter how you change your initial point on the line, you'd still have the same slope, and that would eventually simplify to the same equation. If you're curious, we still can use vectors to represent lines in 2D space instead of analytical equations. So what we're saying, we're going to take this vector r, which is our point on L, is equal to our initial vector or initial position plus a multiple of the direction of our line L. And in this case, all that we change is that our vectors have x and y components only, not x, y, and z components. So that can make things a little bit easier. So if I write each vector in terms of its x and y components, such that our arbitrary point has coordinates x, y is equal to our initial position vector x0, y0 plus t times our vector ab with the two vectors on the right side add together is equal to x0 plus t times a, comma, y0 plus t times b. What we've done here is we've essentially parametrized each component by component with t, instead of changing t and then adding two vectors after that. What we're doing is changing t and changing each component while we change t without the extra addition. Each component is telling the same thing. We have our initial position with respect to that component plus t times the little jump in that component. In general, with any point in 3D space, given a direction vector of the line with components a, b, and c, and an initial point p0 with components x0, y0, z0, any point on line L, call it p with x, y, and z, it can be found through the following parametric equations, which are what these are called. So we have x is an equation of t, y is an equation of t, and z is an equation of t. Remember, each component is just initial value of the component plus t times the jump in that component. And t is going to be the same for all three of these equations. Going back to Desmos, I'm going to show how I originally created our desired line, this gray line that we wanted to get to through our vector representation. So notice how I only have one line in Desmos, and that's all I had to do to represent our gray line. If I unclick it, that's our entire gray line. So this single equation was our line. And instead of doing all this with the vectors, our direction, and our initial vector, what I did was I just had 3 parametric equations represent our x, y, and z points. However, these representations do connect. So notice the first thing I'm going to do is connect the direction vector. If you look at each of the coefficients of t in our parametric representation, we have 1, 3, and 2. Those correspond to the x, y, and z points. Remember, our direction vector is 1, 3, and 2. So that's where the direction vector shows up in our equation. Next thing, we have our initial position. If we look at what we added those jumps of the direction vector to, we added 1, we added 4, and we added 4. If we look at our position vector, our initial position vector, we have 1, 4, and 4. So this goes to show how the vector representation and the parametric representation, they're one and the same. They're just two different ways of showing the same line. A final representation of a line is our symmetric equations. So say I take these parametric equations, and for each component, I'm going to isolate t. Remember, t is going to be the same throughout all these systems. So for each one, it's going to be simply subtracting on one side and then dividing by the coefficient of t. You can notice what that gives for each component. Now, because they're all equal to t, they're all equal to each other. What that gives are these 3 expressions that are all equal to each other, which are equal to t. And this is our symmetric form of our line. Upon first glance, this is a bit confusing as to what it actually represents, but say we're given known values for x0, y0, z0, and a, b, c. If we're given those known values and we put them into the symmetric equations, what that means is every triple of x, y, and z, that point lies on the line. if it satisfies the equation, obviously, because we're probably going to be given a value of t. So every triple of x, y, and z, if it satisfies the equation, it lies on the line. In summary, we've arrived at three representations of lines in space. We have the vector representation, the parametric representation, and the symmetric equation representation of a line. Now we're going to look at how we can actually apply each of those representations in respective contexts. So the first one, and in my opinion, the easiest one, is the vector representation. So here we're given a line that passes through the points 5, 1, and 3. And the direction vector, or the line is parallel to the vector 1, 4, -2. This is pretty straightforward, so we're going to let our initial position be R0, which is the point we're given 5, 1, 3. And then our direction vector be the vector we're given 1, 4, -2. Combining those in the form R0 plus t, our parameter, times our direction vector, we get to 5, 1, 3 plus t multiplied by 1, 4, -2. This is sufficient enough, but if you want to combine them into one vector, you get our point is going to equal 5 plus t, 1 plus 4t, and 3 minus 2t. This can be arrived at with just distributing the t in our direction vector and then adding the final vectors. Again, these are both sufficient answers, depends on which one you want. Now for the parametric and symmetric representations, it's a little less straightforward, but nonetheless, it's still the same basic idea. So here we're given 2 points. Call the first one A with coordinates 2, 4, -3, and our second point B with coordinates 3, -1, 1. What we're asked for is the parametric and symmetric representation of this line, and also where this line, if at all, intersects the xy plane. The first thing we're going to do is find the direction vector. So similar to how we find the slope of a line given 2 points in 2D space in the 2D plane, we're going to subtract the components of the first point from the components of a second point to arrive at the vector between them, which is going to be the direction vector for the line. So given that process, we're going to plug in our values. It doesn't matter which order we do it, but as long as we subtract B from A or A from B, that'll give us our direction vector. What I did was I subtracted the components of A from the components of B. So that gives us 3 minus 2, -1 minus 4, and 1 minus -3. And we'll arrive at 1, -5, 4. So that vector is going to be the direction vector for our line. The next thing we have to do is find our initial position. Luckily, they gave us points on the line. And remember, it doesn't matter where our initial position is, as long as it's on the line and we're adding to it multiples of our direction vector. So for the initial position, we could just use either A or B and make it easier for ourselves. I used point A, which is 2, 4, -3. And this is a vector, not a point. We just converted, this is just a vector representation of the point, or a position vector. So given our values for our direction vector and our initial position, I'm just going to go component by component, or by x and by y and by z for our points on the line. So for x, our x0 plus t times a is going to be 2 multiplied by 1 times t. So we have x is equal to 2 plus 1t. And then for y, we have 4 minus 5 times t. So y is equal to 4 minus 5t. And finally for z, we have -3 plus 4 times t. So we have -3 plus 4t. This is our parametric representation. Now the last thing we have to do is just isolate t in each of these equations and then set each of those equations equal to each other. So for x, we subtract 2 and divide by 1 to get t is equal to x minus 2 over 1. For y, we do y minus 4 divided by -5 is equal to t, which is right here. And then for z, we add 3 and divide by 4. So we have z plus 3 over 4 is equal to t. And this is our symmetric representation of our line. The final thing they ask us to do is find where this line intersects with the xy plane. And this is where the symmetric equation comes in handy. So the xy plane itself in 3D space, it's pretty much all points in space where z is equal to 0. If you can imagine any point on the xy plane, if you let the first two values equal anything, as long as the last value, the z value, is equal to 0, you're on the xy plane. And remember, this symmetric equation is saying all triples x, y, and z that satisfy these equations are points that lie on the line. And given that z is equal to 0, what we're going to do is we pretty much set z equal to 0, and then we're going to solve for x and y. We have when z equals 0, it's going to be 0 plus 3 over 4, which is just 3 over 4. And we go piece by piece, solving for x and y respectively. With x, we have x minus 2 over 1 is equal to 3 over 4. And then just solving for x, we get x is equal to 11 over 4. So that's our x value. For y, we have y minus 4 over negative 5 is equal to 3 over 4. And solving for y, we get y is equal to 1 over 4. We now have our values for x and y, and we know that z is equal to 0. Therefore, we have our point where this line meets the xy plane, which is 11 over 4, 1 over 4, and 0. In this video, we went over how to represent lines in 3D space. The first thing we went over is that you can't use an analytical equation to model a line in space. What that means is you can't have one single equation with a left side equal to a right side that somehow represents a line. That means you would have however many inputs and you spit out an output that would give you a line. That's not true. But in space, what that would do is actually give you a plane, not a line. To fix that problem, the first thing we explored was vector representation. In vector representation, we introduced an important concept called position vectors. And essentially these position vectors are vectors that represent points in space. It seems a little bit counterintuitive and a little pointless, but eventually, this actually showed how a single vector, the way that vectors can hold several pieces of data, we can use vectors in one single equation like we couldn't before to hold data for x, y, and z points and eventually give us one single equation for a line in space. Lastly, we went over parametric and symmetric equations. Parametric equations are essentially using a variable or a parameter to model a line in space, meaning that as we change our parameter, which is usually t for time, it'll give us x, y, and z coordinates in space, therefore giving us a line. And we can, changing what our parameter is, it changes where we are on the line. And from the parametric equations, we arrived at our symmetric equations. They're a little bit more difficult to understand, but the essence of it is that every x, y, and z that satisfy the parametric equations, that triple is on the line. So that x, y, and z coordinate is on the line that we're looking for.